The largest structures in the cosmos are slowly vanishing before our eyes. A supermassive black hole with a mass of billions of suns does not end in a cataclysm. Instead, it fades like a whisper in the void through a process called Hawking radiation. This silent evaporation happens over timescales that defy human imagination, yet it holds the key to the ultimate fate of the universe itself. By the end of this exploration, you will understand how the laws of physics guarantee that even cosmic titans are not permanent. We will uncover what happens when the universe's ultimate sinks of matter and energy begin to leak, and why this slow decay is crucial to solving the deepest puzzles of reality. What does it mean for nothing in existence to last forever? This perfect cosmic trap is the very definition of a black hole, an object so dark it gives the universe its deepest shadow. For decades, this was the absolute truth, a one-way street into oblivion governed by Einstein's vision of gravity. Nothing could challenge it, not even light itself. But then came a whisper from the quantum world, a realm where different rules apply. Here, the idea of true emptiness does not exist. What we perceive as the void of space is, at the tiniest scales, a turbulent ocean of potential. Pairs of particles and their anti-particle counterparts flicker into existence for the briefest moments, borrowing energy from the universe before annihilating each other and paying the debt back. This constant, ghostly activity is usually invisible, a balanced ledger of creation and destruction. But place this quantum froth at the precipice of an event horizon, and the balance is shattered. Imagine one of these virtual pairs appearing right at the edge. Through a strange twist of quantum chance, one particle could fall across the point of no return, while its partner is flung outward into space. The particle that escapes becomes real, carrying away a sliver of energy. And since energy and mass are equivalent, that stolen energy comes directly from the black hole itself. This is Hawking radiation, a faint glow predicted not by the laws of gravity, but by the bizarre rules of the quantum vacuum. The black hole, the ultimate symbol of darkness, is not completely black after all. It possesses a temperature, an almost impossibly faint heat signature born from the chaos at its boundary. This subtle glow does more than just redefine these objects. It plants the seed of their ultimate destruction, a process so slow it makes the age of the universe seem like a blink. This faint glow is born from a cosmic trick, a sleight of hand played by the universe's own rules at the very edge of reality. To understand it, picture not the dark silence of a black hole, but the roaring, chaotic energy at the base of a waterfall. The water has crossed a point of no return, plunging into a turbulent pool where foam and spray are violently churned into the air. The event horizon is that precipice, and the fabric of space-time itself is the river, stretched and twisted by immense gravity. In that region of extreme curvature, the quantum vacuum is not calm. The raw gravitational energy is so intense it can act like a cosmic boost, lending the fleeting virtual particle pairs enough energy to become real. They are no longer ghosts that instantly vanish. They are momentarily pulled into existence by the sheer force of the distorted space around them. Now for the trick. If this newly realized pair appears right at the boundary, a strange fate can befall them. One particle, carrying what we can think of as negative energy, gets swept across the horizon, falling inward. Its partner, now carrying positive energy, is propelled outward, escaping into the universe as a genuine piece of radiation. The key is that the negative energy particle reduces the total mass energy of the black hole, while its escaped twin carries that stolen energy away forever. This is not some fiery jet erupting from the depths. It is a quiet, statistical process happening in the violent quantum froth right at the precipice, a boundary effect that slowly siphons mass from the cosmos' most perfect trap. The radiation that escapes is thermal, meaning it has a very specific character, like the dull red glow of a cooling ember. Its temperature is tied directly to the black hole's size, and here lies a profound and counterintuitive truth. The temperature is inversely proportional to the mass. A smaller, less massive black hole would actually be hotter, glowing more intensely with this Hawking radiation. For the stellar mass black holes we know, this temperature is unimaginably cold, just a fraction of a degree above absolute zero, utterly drowned out by the cosmic microwave background. But the principle is established and it is ironclad. Through this quantum mechanism, a black hole is not a permanent fixture, it is a slowly leaking vessel. The largest ones, the supermassive giants at the hearts of galaxies, leak the slowest of all, their evaporation so gradual it unfolds over timescales that challenge the meaning of time itself. This leads us to a staggering implication. If the process is continuous and unending, what happens when the leak becomes a flood? This inverse relationship between size and heat is one of the most bizarre ideas in all of physics. In our everyday world, bigger objects hold more heat. A bonfire is hotter than a match, but black holes defy this intuition completely. A black hole with the mass of our Sun would have a Hawking temperature of about 60 nanokelvins. That is 60 billionths of a degree above absolute zero, a chill so profound it is almost a philosophical concept rather than a measurable warmth. Now, take that solar mass black hole and make it 10 times heavier. Its temperature does not rise, it plummets to 1/10 of that already unimaginable cold. Make it 100 times heavier, and the temperature drops to 1/100th. The more mass a black hole swallows, the colder and quieter it becomes. This is why the true giants of the cosmos are the most silent. Consider Sagittarius A star, the supermassive black hole at the heart of our own Milky Way. It weighs in at roughly 4 million times the mass of our Sun. Using that same inverse relationship, its Hawking temperature becomes not just cold, but an almost meaningless number, a tiny fraction of a microkelvin. At that point, the radiation it theoretically emits is so incredibly feeble, so whisper-thin, that it is utterly and completely drowned out by every other source of energy in the universe. The afterglow of the Big Bang, the light from distant stars, even the faint infrared glow from cosmic dust, all of these are roaring signals compared to the silent evaporation of a galactic core. This is the first crucial piece of the puzzle explaining their slow fade. They are not just large, they are profoundly cold because of their immense size, leaking energy at a rate so slow it is, for all practical purposes, a standstill. Their evaporation is a process of such staggering patience that it unfolds on a timescale we have no words for, a duration that makes the current age of the universe seem like the first spark of a flame. To grasp that timescale, we must move from temperature to time and confront numbers so large they bend our understanding of reality itself. The mathematics behind this decay reveals a timeline that stretches the definition of eternity. The time it takes for a black hole to completely evaporate is not just long, it is proportional to the cube of its mass. This simple relationship has staggering consequences. For a typical black hole born from a collapsed star, about 3 times the mass of our Sun, the calculation yields a number so large it defies everyday analogy, approximately 10 to the power of 67 years. That is a 1 followed by 67 zeros. To even begin to grasp this, consider that the entire current age of our universe is only about 13.8 billion years, a number with a mere 10 zeros. The evaporation of a single stellar corpse takes a duration 10 million trillion times longer than the cosmos has even existed. Now apply that cubic rule to a true cosmic titan, a supermassive black hole with the mass of 1 billion suns, like those found in the hearts of large galaxies. Cube that billion solar mass figure. The resulting timescale is a number so astronomically vast it makes the lifetime of a star-sized black hole seem brief. We are talking about a duration that dwarfs the current age of the universe by a factor of billions upon billions. This is not merely a long wait, it is a timescale that exists in the realm of theoretical cosmology's farthest future. By the time a supermassive black hole even begins to fade in earnest, every star in every galaxy will have burned out and gone dark. The galaxies themselves will have drifted apart into an expanding, lonely void. Even the very protons that make up all matter may have decayed, leaving behind a sea of fundamental particles and radiation. The evaporation of these giants is a process that belongs to an epoch so distant, it redefines our understanding of an ending. Yet, if we could somehow fast forward to that almost mythical era, the final act of a black hole's life would be anything but silent. But this profound silence is not the end of the story. There is a cosmic battle happening right now, a quiet tug of war that is actively working against evaporation. Our universe is not an empty, cold void. It is filled with a faint, pervasive glow, the afterglow of the Big Bang itself. This is the cosmic microwave background radiation, a bath of photons that permeates every cubic inch of space with a temperature of about 2.7 Kelvin. That is 2.7 degrees above absolute zero, a gentle warmth compared to the unimaginable cold of a supermassive black hole's Hawking radiation. And here lies the critical delay, right now, and for an almost unthinkable length of time into the future. Every black hole in the cosmos is soaking up this background radiation. They are absorbing these ancient photons at a rate that completely overwhelms their own feeble Hawking emission. Think of it like a leaky bucket sitting out in a very light, persistent rain. The few drops leaking out from the bottom are the Hawking radiation, but the rain falling into the top, the cosmic microwave background, is a steadier, stronger drizzle. For now and for eons to come, the bucket is not emptying. It is slowly, imperceptibly filling up. These cosmic giants are not yet evaporating. They are still gaining mass, fed by the fading warmth of creation itself. For true evaporation to finally begin, the universe itself must change. It must expand and cool so much that the temperature of this cosmic background bath drops below the even colder temperature of the black hole's own Hawking glow. Only then will the absorption stop and the net loss begin. Current models suggest this pivotal crossover, where the universe finally becomes cold enough for black holes to start losing the battle, will not occur for another trillion years at the very least. So the silent evaporation we've been discussing is not just a slow process. It is a process that has not even properly started yet. The largest structures in existence are currently in a state of suspended animation, their fate held in check by the fading echo of the universe's birth. This pushes their final act into a future so remote it challenges our very concept of time. And when that distant epoch finally arrives, the end will be anything but a quiet fade to black. The quiet leak becomes a torrent in its final moments. After an almost eternal slumber, the mathematics of evaporation takes a dramatic turn. Remember the inverse relationship, where a smaller black hole is a hotter one. As the black hole steadily loses mass through Hawking radiation, that very loss causes its temperature to climb. A higher temperature means it radiates energy away even faster, which causes it to lose mass more quickly, which increases the temperature again. This creates a runaway feedback loop, a crescendo of self-destruction. The process, glacial for nearly all of its existence, begins to accelerate exponentially. For the last fraction of its life, the silent cosmic pit transforms into a brilliant, searing beacon. Consider a black hole that has evaporated down to the mass of a large mountain. In its final second of existence, it would not be cold and dark. It would glow with unimaginable ferocity, releasing energy equivalent to the detonation of millions of hydrogen bombs all at once. This final flash would be a torrent of high-energy gamma rays and particles, a brief but spectacular shout into the void after an eon of silence. This is the only loud chapter in a story written almost entirely in whispers. For a supermassive black hole, the journey to this point is almost beyond comprehension. It spends over 99.999% of its total lifespan in that state of cold, imperceptible dimming, its evaporation rate utterly negligible. The final explosive phase, while violent and luminous, is over in a cosmic instant, a fleeting spark at the end of an ocean of time. This stark contrast defines their existence, a near-eternal quietude punctuated by one final, brilliant, and definitive release. It raises a profound question about what, if anything, remains when that final flash of light fades from the cosmos. That final brilliant flash presents a frustrating paradox for astronomers. We have a rock-solid theoretical prediction, one that reshapes our understanding of gravity and quantum mechanics, yet we have never directly seen it happen. The challenge is not one of theory, but of sheer scale and the cold, quiet nature of the universe itself. To observe Hawking radiation from an actual black hole, our instruments would need to detect a signal of unimaginable weakness. For a stellar mass black hole, the Hawking glow is billions upon billions of times fainter than the cosmic microwave background, that faint afterglow of the Big Bang that fills all of space. It is like trying to hear a single snowflake land in the middle of a roaring hurricane. The supermassive black holes are even colder, their theoretical radiation so feeble it is lost in the noise of the cosmos, drowned out by the light of stars, the glow of dust, and the chatter of every other energetic process in the galaxy. Over the human timescales of a scientific career, or even the entire history of astronomy, the change in a black hole's mass due to this evaporation is utterly undetectable. We are trying to measure the evaporation of a mountain by watching a single grain of sand blow away over 1,000,000 years. So if we cannot see it directly in the cosmos, how do we know it is real? The scientific journey turns from the telescope to the laboratory, seeking not the phenomenon itself, but its echoes in other forms. Researchers have created remarkable analog black holes in controlled settings. One powerful analogy uses sound. In a carefully engineered fluid flowing faster than the speed of sound, scientists can create an acoustic event horizon, a point of no return for sound waves. Ripples in the fluid representing particles can be trapped inside this sonic horizon while their partners escape, creating an analog of Hawking radiation made not of light but of sound phonons. Other experiments use pulses of light in special optical fibers or ultra-cold clouds of atoms, all designed to mimic the extreme warping of space-time at an event horizon. In these tabletop universes, researchers have detected the telltale signatures of particles being generated from the quantum vacuum at these artificial horizons. These are not black holes evaporating, of course, but they demonstrate the core quantum mechanical principle that underpins the entire theory. They show that under the right conditions of extreme distortion, the vacuum can indeed give birth to real particles. This gives physicists tremendous confidence that the same mathematics, when applied to the gravitational precipice of a real black hole, must hold true. So while we may never point a telescope and see a black hole gently steaming away into the void, the effect is considered a cornerstone of modern theoretical physics. It is a prediction that ties together the two great pillars of 20th century science, general relativity and quantum mechanics, in a way that nothing else does. This forces us to confront an even deeper mystery, one that lies at the heart of the evaporation process itself. If information is what makes a universe knowable, what happens to all of it when a black hole finally vanishes? This paradox strikes at the very heart of our understanding of reality. For decades, physicists have grappled with a fundamental conflict between two of their most successful theories. On one side, quantum mechanics, the rulebook for the subatomic world, has a sacred principle: information cannot be destroyed. Think of it like this: if you burn a book, the paper turns to ash and smoke. But in principle, if you could collect every particle of ash and trace of gas and analyze them with perfect knowledge, you could reconstruct the original book. The information, the specific arrangement of letters and words that told a story, is not gone. It is just scrambled into a different form. This principle of information preservation is a cornerstone of how we believe the universe operates. On the other side stands the classic picture of a black hole born from Einstein's general relativity, combined with Stephen Hawking's own early calculations about evaporation. In that view, when matter falls into a black hole, all the information about that matter, what it was made of, its structure, its history, is completely and utterly lost behind the event horizon. Then, when the black hole evaporates via Hawking radiation, what comes out is purely random thermal energy, like the featureless glow from a hot stove. It carries no fingerprints, no hidden code, no trace of the stars, planets, or atoms that fell in. According to this story, the black hole is the universe's ultimate shredder, not just of matter, but of information itself. This is the black hole information paradox, a direct contradiction between two pillars of physics. It suggests that our theories, as brilliant as they are fundamentally incomplete where gravity and quantum mechanics meet. The evaporation process is not just a slow fade, it is the stage for this epic confrontation. So where does the information go? Could it truly vanish from existence, violating a law we hold as universal? Or is our picture of the event horizon and of the radiation itself somehow wrong? Recent thinking has tilted dramatically toward the latter. One compelling idea suggests that information is never actually lost inside. Instead, it might be preserved in a way that challenges our intuition about space. The holographic principle proposes that all the information describing everything within a three-dimensional volume of space can be perfectly encoded on its two-dimensional boundary, like a cosmic DVD. For a black hole, that boundary is the event horizon. In this view, when an object falls in, it does not simply disappear into a point. Its information is smeared and imprinted onto the horizon itself, altering it in subtle, quantum ways that some physicists poetically call quantum hair. Then, as the black hole evaporates, this encoded information is slowly, intricately transmitted out into the Hawking radiation. The radiation would not be purely random and thermal after all. It would contain subtle correlations, a faint but complex pattern woven into its glow that, in principle, holds the story of everything that ever fell in. Decoding that pattern from the faint whisper of radiation is a task of almost unimaginable difficulty, but the mathematics suggests it could be possible. This means the evaporation is not an erasure, but a transformation, a translation of information from one form to another. The paradox forces us to see black holes not as endpoints, but as perhaps the most extreme information processing systems in the cosmos. Their slow, silent fade, the final act of a cosmic story that never truly ends. While the supermassive giants slumber in near-permanent cold, there exists another, more ghostly class of black hole where evaporation is not a distant theory, but a potential present-day firework. These are the primordial black holes, and they turn the timescale of decay on its head. Unlike the black holes born from dying stars, these are relics of the universe's first chaotic moments. In the intense heat and density just after the Big Bang, tiny pockets of space could have collapsed under their own weight, forming black holes of almost any size. Some could be as massive as planets, while others might be no heavier than a large mountain or even an asteroid. Their size makes all the difference. Remember that critical rule: the smaller the black hole, the hotter it glows. A primordial black hole with a mass around 1 billion metric tons, which is roughly the mass of a modest mountain here on Earth, would have a temperature of over 1 billion degrees Kelvin. At that staggering heat, it would not be a silent, cold object. It would be a brilliant, seething sphere, radiating away its mass at a furious pace. For such a small, hot black hole, the entire multi-trillion-year lifespan of a supermassive giant is compressed into a mere cosmic blink. Its evaporation would be nearly complete within the current age of the universe. Right now, as we speak, black holes of this size could be reaching the explosive finale of their lives somewhere in the cosmos. That final flash, a burst of high-energy gamma rays, would be their death cry. This is not a quiet theoretical whisper, it is a potentially observable signal. Astronomers have scanned the skies for years, searching for the telltale signature of these miniature black holes exploding. They look for brief, sharp bursts of gamma rays that don't match the profile of known events like collapsing stars or merging neutron stars. A confirmed detection would be one of the most profound discoveries in modern physics. It would do more than just prove primordial black holes exist. It would provide direct, observational evidence for Hawking radiation itself, turning a brilliant theoretical prediction into a documented fact of the cosmos. These tiny, evaporating candidates are the crucial testing ground. They offer us a tangible, if elusive, window into the same slow-motion fate awaiting the largest structures in existence. By studying the possible explosive end of the smallest black holes, we gain essential clues about the ultimate destiny of the largest. This connection between the tiny relics of creation and the titans at galactic centers forces us to ask a broader question about the universe's own timeline. If all black holes, great and small, are destined to fade, what does that mean for the cosmos itself far, far into the future? The silent evaporation of black holes may hold clues to one of the greatest cosmic puzzles, the nature of dark matter. This mysterious substance, which outweighs all visible matter 5-to-1, has eluded every direct attempt at detection. But what if dark matter is not made of unknown particles, but of the final, stable remnants of long-dead black holes? This speculative idea emerges from the mathematics of Hawking radiation. As a black hole shrinks toward its final explosive flash, the radiation becomes more energetic. Yet when the black hole's mass becomes incredibly tiny near the Planck-Scale, our current laws of physics break down. At this point, some theories suggest the evaporation might simply stop, leaving behind a stable, microscopic relic with a mass roughly equal to the Planck mass, a minuscule 20 micrograms. These relics would be incredibly dense, nearly indestructible, and would not interact with light or ordinary matter, making them virtually invisible, perfect candidates for a component of dark matter. While this remains a fascinating hypothesis, it illustrates a profound point. The study of black hole decay is not an isolated curiosity. It forces us to confront the limits of our knowledge and pushes us toward a more complete picture of reality, where the fate of the largest structures is intimately tied to the behavior of the universe at its smallest possible scales. This journey to the smallest scales opens the door to even more radical possibilities, such as the existence of extra dimensions. In our familiar 3 dimensions of space, gravity is the weakest force, which is why Hawking radiation is such a faint process. But some unified theories, like string theory, propose that the fabric of our universe is woven with more spatial dimensions than we can perceive. These extra dimensions could be curled up and hidden at scales far smaller than an atom. Crucially, in such a model, gravity might not be weak at all. Its strength could be diluted because it spreads out into these unseen dimensions. At the incredibly small scales approaching a black hole's final moments, gravity's true power might be revealed. This would dramatically alter the equations for Hawking radiation. A microscopic black hole in a universe with extra dimensions could evaporate not with a slow whisper, but in a sudden, violent burst of high-energy particles, potentially observable by our telescopes today. The search for these final flashes becomes a double hunt. for both evaporating black holes and for evidence of the hidden architecture of spacetime itself. Every calculation about a black hole's slow fade rests on our assumptions about gravity, quantum mechanics, and the very nature of reality. By probing this ultimate evaporation, we are not just predicting a distant cosmic fate, we are stress testing our most fundamental theories against the most extreme conditions the universe can provide. The silent end of a black hole, therefore, might be the key that unlocks a much louder truth about everything. This timeline of decay forces us to look beyond the lifespan of any single object to the ultimate fate of the cosmos itself. Cosmologists chart the universe's future in vast chapters, each defined by the dominant source of light and structure. We currently live in the stelliferous era, a time rich with the glow of stars and the birth of galaxies. But this era is fleeting on a cosmic scale. In roughly 100 trillion years, the last stars will flicker out, their fuel exhausted. The universe will enter the degenerate era, a profoundly darker age dominated by the cooling embers of dead stars, white dwarfs and neutron stars, slowly radiating their remaining heat into an ever colder and emptier void. And after that, when even those faint glows have faded after quadrillions upon quadrillions of years, the final great age will begin, the black hole era. During this unimaginably long epoch, spanning timescales that make our current universe seem infantile, the only significant sources of luminosity will be the Hawking radiation from evaporating black holes. The supermassive giants, having feasted on stars and gas for eons, will finally stand alone as the last organized structures in an otherwise dark and nearly empty cosmos. Their slow, silent evaporation will become the primary source of activity, the last flickering candles in an expanding abyss. This era is not a place of sudden drama, but of profound and patient transformation. The universe will be a cold, near-perfect vacuum, its temperature having plummeted far below even the faint warmth of today's cosmic background. In that deep freeze, the black holes will at last begin to lose mass faster than they can absorb stray photons. One by one, over durations we can write down but cannot truly feel, these titans will dim and shrink. Their Hawking glow will start as an imperceptible whisper, then gradually brighten over epochs as they lose mass and heat up, each one culminating in that final, brilliant flash of gamma rays. The black hole era is a chapter written in the slowest possible ink, a testament to the fact that even in a universe destined for darkness and dispersion, change is the only constant. Mapping this distant future is not mere speculation. It is a crucial exercise in understanding the full implications of the laws of physics we see at work today. The silent evaporation we have been tracing is the central plot of this ultimate cosmic story. The most profound truths about these cosmic giants are written not in their gravity, but in their heat. To truly grasp their slow evaporation, we must see them not as monsters in the dark, but as the universe's most perfect and paradoxical heat engines. This shift in perspective came from a stunning connection between the warped space of a black hole and one of physics' most sacred laws, the second law of thermodynamics. This law states that in any closed system, entropy, which is a measure of disorder or the number of possible arrangements, always increases. Things tend toward messiness. For decades, black holes seemed to be the ultimate violators of this law. You could throw a perfectly ordered, low-entropy object, like a pristine diamond or a complex computer, into a black hole, and it would vanish, seemingly erasing that entropy from the universe. This troubled a young physicist named Jacob Bekenstein. He proposed a radical solution. What if the entropy was not destroyed, but was instead carried by the black hole itself? He calculated that a black hole's entropy is not found in its volume, but is engraved directly onto its surface, the event horizon. The entropy is proportional to the area of that horizon. The larger the black hole, the greater its surface area and the more entropy it contains. This was a revolutionary idea, suggesting that all the information about everything that ever fell in was somehow smeared across this two-dimensional boundary. But Bekenstein's theory had a glaring hole. In thermodynamics, anything that possesses entropy must also have a temperature, and a temperature implies an ability to radiate heat. At the time, everyone knew black holes were defined by their inability to radiate anything. They were perfect absorbers. This is where Stephen Hawking entered the story. His calculation of Hawking radiation provided the missing piece. That faint quantum glow was not just radiation, it was thermal radiation with a precise temperature. Hawking's work confirmed that black holes do indeed have a temperature, and it is exactly the temperature required to make Bekenstein's entropy formula consistent with the laws of thermodynamics. In one stroke, black holes were demoted from cosmic rule breakers to obedient participants in the universe's grand thermodynamic dance. They became heat engines, objects that convert mass energy into thermal radiation according to strict physical laws. Their slow evaporation is simply the ultimate expression of this. It is the process by which a black hole, a pocket of incredibly high entropy and energy, gradually radiates that energy away into the colder surrounding universe, moving toward a state of thermal equilibrium. It is the heat death of the object itself. From this viewpoint, the supermassive black hole at a galaxy's heart is not just a gravitational anchor, it is a reservoir of cosmic disorder, slowly and patiently dissipating over eons. This thermodynamic lens elevates them from mere curiosities to essential characters in the story of cosmic evolution. They are not just sinks for matter, but active participants in the universe's long, slow journey toward maximum entropy. A journey where even the darkest objects must eventually share their heat with the void. This thermodynamic story is written not just in heat, but in the very shape of the universe. The silent evaporation of a black hole is a process of subtraction, a slow removal of mass from a specific point in space. And in Einstein's universe, mass does not just sit there, it warps the fabric of spacetime itself, creating the gravity we feel. So what happens to that warp when the mass causing it slowly disappears? The geometry of spacetime around the black hole must adjust, must smooth itself out as the central weight diminishes. This adjustment would not be silent in the language of gravity. In theory, it could create ripples. As the black hole's mass ebbs away, the change in its gravitational field might propagate outward as an unimaginably faint whisper of gravitational waves. These would not be the powerful chirps from colliding black holes that our observatories detect today. This would be something far more subtle, a nearly monotone hum decreasing in amplitude over eons, a direct sonic imprint of the evaporation process itself. Detecting such a signal borders on the impossible with any technology we can conceive. It would be billions of times weaker than the faintest ripple we currently hunt for, buried under the noise of the cosmos itself. Yet the principle holds a profound elegance. It suggests that a black hole's farewell is not communicated through a single channel. It may broadcast its slow demise in a symphony of emissions, a faint thermal glow in the electromagnetic spectrum paired with an even fainter tremor in the gravitational fabric of the cosmos. This multi-messenger farewell, however, might save its crescendo for the very end, the final explosive instant of a black hole's life, when it converts its last remaining mass into a flash of high-energy radiation, would be an event of staggering violence and change. In that split second, an enormous concentration of mass energy vanishes from the universe. Such a rapid, asymmetric disappearance could, in theory, generate a unique burst of high-frequency gravitational waves, a final, sharp pop in the spacetime continuum marking the exact moment the cosmic pit winks out of existence. This is a highly speculative idea, but it beautifully connects the two great revolutions in how we observe the universe, light and gravity. It proposes that even in their quietest, most patient fading, black holes may be writing their epitaph not just in photons, but in the subtle vibrations of space itself, leaving a dual signature for a future civilization with sensors vast enough to perceive it. The silent evaporation of a black hole is a story written in the language of endings. It forces us to confront a truth that reshapes our cosmic perspective. Nothing in this universe is built to last. For centuries, black holes stood in our collective imagination as the ultimate symbols of permanence. They were the final stop, the inescapable fate, the eternal prisons from which not even time could escape. They represented a kind of grim cosmic certainty, the one thing you could always count on to be there, consuming, anchoring, enduring. Hawking radiation dismantles that certainty. It tells us that even these monolithic giants are subject to the same universal laws of decay that govern everything else, from the mightiest mountain to the most fleeting thought. They are not endpoints but waypoints in an unimaginably long journey of transformation. Their immense gravity and apparent stillness are an illusion of scale, masking a slow but inexorable process of dissolution. This introduces a profound note of impermanence into the heart of the cosmos. It aligns with a principle found in ancient philosophies, that all compounded things are subject to change and dissolution. On a physical level, it is the ultimate expression of the second law of thermodynamics, not just in a lab or a star, but on the grandest stage imaginable. Entropy always increases, disorder always grows, and given enough time, every structure, no matter how seemingly eternal, will unravel. The supermassive black hole at a galaxy's core is not a permanent monument. It is a temporary configuration of energy, a knot in space-time that will, over an ocean of eons, slowly untie itself. Its silent evaporation is the universe patiently erasing its own boldest signature. This cosmic impermanence suggests a cyclical nature to existence itself. If the mightiest structures arise from chaos, feast for an epoch, and then slowly dissolve back into a formless sea of quantum potential, then what we see as the stable universe of galaxies and stars is merely a phase, a temporary pattern in an endless dance of formation and dissipation. The black hole's fade does not lead to nothingness but to a return. The mass energy locked within its event horizon is not destroyed. It is meticulously transformed and released back into the cosmos as radiation, ready to potentially fuel new cycles of creation in a future so distant it defies all narrative. This transforms our view from one of fixed hierarchy to one of dynamic flow. We are not living in a universe of permanent fixtures, but in a universe of processes, of becoming and unbecoming, where even the darkest abyss holds within it the seed of its own luminous end. The lesson written in their slow fade is humbling and expansive, a reminder that change is the only true constant, woven into the fabric of reality from the quantum scale to the galactic core. The story of their slow fade is not just told in words, but in a language of profound elegance, the language of mathematics. At the heart of this cosmic process are a few deceptively simple equations, a quiet symphony of symbols that unify the universe's deepest laws. The first gives the Hawking temperature. It states that the temperature of a black hole is equal to a combination of fundamental constants divided by its mass. The numerator contains the reduced Planck constant from quantum mechanics and the speed of light cubed from relativity. The denominator features Newton's gravitational constant and the Boltzmann constant from thermodynamics. This single, compact formula is a masterpiece of synthesis. It tells us that the heat of a black hole is dictated by the tug of war between the quantum fuzziness of empty space and the relentless pull of gravity. The smaller the mass in the bottom, the larger the resulting temperature, confirming that smaller black holes truly are hotter. From this temperature, we can derive its luminosity, the power it radiates away. This power is proportional to the square of the temperature, which, through the first equation, becomes inversely proportional to the square of its mass. A black hole half the size doesn't just glow a little brighter, it shines with 4 times the power, accelerating its own demise. This relationship feeds directly into the final, pivotal equation, a differential equation that describes the rate of mass loss. It tells us that the change in mass over time is negative and proportional to 1 over the square of the current mass. This is the engine of the feedback loop. As mass decreases, the rate of loss increases, which decreases the mass further, sending the process into its final runaway crescendo. The beauty of these equations lies not in their complexity, but in their unity. They are not separate rules from different branches of physics forced together. They are a seamless blend, showing that quantum mechanics, gravity, and thermodynamics are not independent chapters in a textbook, but different verses of the same cosmic poem. Written on a page, they are a sparse arrangement of symbols, but in their application, they describe the entire multi-trillion-year life cycle of a cosmic titan, from its cold, silent dominance to its final brilliant flash. They offer a tangible framework, a set of precise relationships that transform a mind-bending concept into a calculable destiny. For all their quiet power, however, these equations point toward a moment where our current understanding dissolves into mystery at the very precipice of nothingness. Yet for all its mathematical elegance, Hawking's prediction lies in a theoretical frontier. The equations are clear and compelling, but they rest on a foundation that itself remains incomplete. We are applying the rules of quantum field theory, which work flawlessly in the flat, gentle spacetime of a laboratory, to the wildly curved, violent geometry right at the edge of an event horizon. This is a daring extrapolation, a brilliant piece of theoretical stitching that joins 2 separate fabrics of physics. The result is a coherent picture, but it is a picture painted before we fully understand the canvas. The complete theory of quantum gravity, a framework that seamlessly unifies the very large and the very small, remains the holy grail of modern physics. Until we have that final theory, or until we observe the phenomenon directly, absolute certainty remains just out of reach. This is not a weakness of the idea, but a testament to the rigorous, self-correcting nature of science itself. Competing approaches to quantum gravity, like loop quantum gravity or various string theory models, sometimes propose subtle tweaks to the story. They might alter the precise spectrum of the radiation, or suggest different behaviors for a black hole in its final moments. Some even explore the possibility that what we call an event horizon might be replaced by a different kind of boundary, a firewall of intense energy or a fuzzy transition layer where our classical notions of space and time break down completely. In these alternative visions, the journey of evaporation might follow a different path, though the destination, the eventual dispersal of the black hole's mass energy, often remains. This landscape of competing ideas is not chaos, it is the essential process of discovery. Hawking's work set a towering benchmark, a specific, testable prediction that every subsequent theory must now confront. The real strength of his radiation is not that it is the only possible idea, but that it is a concrete, mathematically beautiful idea that emerged from first principles. It makes a firm statement about how the universe should behave at this extreme intersection. This creates a target, future observations, perhaps of those primordial black hole explosions, or of subtle effects in the gravitational waves from merging black holes, will aim for that target. If we detect a signal that matches Hawking's precise prediction, it will be a monumental validation. If we detect something that deviates from it, that will be equally monumental, pointing the way toward the new physics that lies beyond our current understanding. So the question of certainty is framed by the scientific method itself. The theory is robust, influential, and widely accepted because it is the best answer we have from our current knowledge. It passes every theoretical stress test we can apply with the tools we possess. But the final verdict, as with all profound truths about the cosmos, will be delivered not by a chalkboard but by the universe. Our task is to keep listening for that faint, final flash in the dark, a whisper that could confirm a brilliant human intuition or guide us toward an even deeper truth. This paradox demands a resolution that reimagines the very nature of reality. The holographic principle offers a breathtaking possibility, one that suggests the information is never truly inside the black hole at all. The name comes from an everyday object, a security hologram on a credit card. That shimmering, three-dimensional image is not carved into the plastic, it is encoded on a flat, two-dimensional surface. The principle proposes that our universe might operate in a similar, though far more profound way. The physics of a three-dimensional volume with all its stars, planets, and the space between them could be entirely described by information stored on its two-dimensional boundary. For a black hole, that boundary is the event horizon. In this radical view, when an object crosses that threshold, it does not simply vanish into a singularity. Instead, its information, the complete quantum description of what it was, gets smeared and imprinted onto the horizon itself. The surface area increases slightly, encoding that new data like a cosmic hard drive. The interior becomes a kind of projection, a holographic illusion built from the data on the surface. This means the black hole's immense entropy, which Bekenstein calculated, is not a measure of internal chaos, but literally the amount of information painted across its spherical shell. The more it consumes, the more intricate that surface painting becomes. This transforms the entire evaporation process. As the black hole radiates via Hawking radiation, it is not emitting random thermal noise. It is meticulously reading out the information encoded on its shrinking surface. The radiation carries subtle, non-thermal correlations, intricate patterns woven into the glow that, in principle, hold the complete story of everything that ever fell in. The evaporation is no longer a destructive erasure, but an incredibly slow and complex translation, a decoding of cosmic data from a two-dimensional format back into the radiation of three-dimensional space. It is as if the universe, faced with its own ultimate shredder, devised a failsafe, backing up all the data on the outside of the machine before anything entered the blades. This idea does more than solve a paradox. It suggests that our perception of a three-dimensional world may be a magnificent illusion, a hologram generated from a vast, interconnected network of information living on the distant surfaces that contain us all. The holographic solution points toward an ending where information is preserved, but it leaves one terrifying possibility on the table. What if the evaporation strips away the event horizon itself, exposing the infinitely dense singularity at the core? This is the ultimate cosmic taboo, a scenario so unsettling that physicists have given it a name, the naked singularity. Our current laws of physics break down completely at a singularity. It is a point of infinite density where space and time, as we understand them, cease to exist. In a normal black hole, this monstrous flaw in reality is safely locked away behind the event horizon, a protective curtain that shields the rest of the universe from its irrational physics. This idea is so fundamental it is enshrined in a principle called cosmic censorship. The hypothesis proposed by Roger Penrose suggests that nature abhors a naked singularity. The laws of physics, it is argued, always conspire to wrap these infinite points in an event horizon, censoring them from the wider cosmos. It is a cosmic fail-safe, preventing the unpredictable madness of a singularity from influencing the orderly universe outside. But the slow evaporation of a black hole poses a direct challenge to this principle. As the black hole loses mass and shrinks, its event horizon also shrinks. The protective curtain is drawn inward. If the evaporation continues all the way to zero mass, the mathematics suggests the horizon would vanish entirely, potentially leaving the naked singularity exposed for a fleeting instant before it too dissipates. This would be a catastrophic violation of cosmic censorship, unleashing a point of infinite curvature upon the universe with no horizon to contain its effects. The consequences are purely theoretical, but they are profound. Causality could break down, the predictable flow of cause and effect could become meaningless. Physics, as we know it, would lose its predictive power at the sight of this exposure. Most researchers believe this simply cannot happen. Nature must have a final trick to preserve the cosmic censor. One compelling possibility is that the evaporation process itself provides the solution. The final explosive burst of radiation, that brilliant flash of gamma rays, might not just be the black hole's death cry. It could be the mechanism that destroys the singularity entirely, leaving no naked core behind. In this scenario, the black hole converts the last of its mass energy so completely that nothing, not even the singularity, remains. Another idea is that evaporation stops just short of zero, leaving behind a stable, microscopic remnant, perhaps a Planck mass particle that permanently encapsulates the singular point, forever keeping it hidden. The evaporation of a black hole, therefore, is not just a test of quantum mechanics and thermodynamics. It is the ultimate experimental test for the principle of cosmic censorship itself. By tracing the mathematical path of a fading black hole, we are asking whether the universe possesses a deep-seated aversion to exposing its own deepest flaws. The silent fade of a cosmic giant becomes a high-stakes drama, a slow-motion unveiling that, according to our best understanding, must always be interrupted at the last possible moment by a law we do not yet fully comprehend. Our simple story of a silent, spherical fade is a beautiful starting point, but the cosmos rarely deals in perfect simplicity. The black holes we've been describing, the ones defined only by their mass, are called Schwarzschild black holes. They are the pristine textbook case, perfectly symmetric and utterly still. But our universe is a place of spin and charge, of dynamic motion and fierce interactions. Real black holes, especially the supermassive ones forged from the chaotic mergers of galaxies and the accretion of swirling gas, are almost certainly not so placid. They are cosmic dynamos spinning at a significant fraction of the speed of light, and they may carry immense electric charge. To understand their true evaporation, we must step into the more complex and fascinating worlds described by the Kerr and Reissner-Nordström solutions. A Kerr black hole is one that rotates. This spin warps the spacetime around it in a dramatic way, dragging the very fabric of the universe around like a whirlpool. It creates two distinct boundaries, not just one. There is the event horizon, the point of no return, but outside of that lies a region called the ergosphere, a zone where spacetime itself is pulled along faster than light. Within this ergosphere, nothing can stand still. The rotation is so powerful it forces everything to move. This has a direct and profound impact on the process of evaporation. In this whirling region, a phenomenon called super-radiant scattering can occur. Imagine a wave of any kind, even a gravitational wave, entering the ergosphere. If the wave has the right frequency, it can be amplified by the black hole's rotational energy, stealing a bit of that spin and escaping with more energy than it arrived with. It is like a surfer catching a perfect wave, being propelled forward with greater force. This is not Hawking radiation per se, but a separate, classical process by which a rotating black hole can lose its angular momentum, its spin, before it even begins to seriously lose its mass. The black hole's furious rotation acts as a reservoir of energy that can be tapped, slowing its spin down long before its mass starts to steadily drain away. Meanwhile, a Reissner-Nordström black hole is one that possesses electric charge. This charge alters the geometry of the event horizon, and it introduces a new player into the quantum vacuum around it. The Hawking radiation emitted by such a black hole would not be neutral. It would preferentially emit particles that carry away the black hole's charge. Positively charged black holes would emit more positively charged particles like protons or positrons in an effort to neutralize themselves, so the evaporation becomes a two-stage process, first shedding its electric charge, then its mass. Now picture the most realistic case, a supermassive black hole that is both spinning furiously and potentially charged. Its evaporation is not a single, silent trickle of thermal radiation. It is a layered, intricate dance. First, through super-radiant scattering and charged particle emission, it would bleed off its angular momentum and neutralize its charge. These processes could be far more efficient initially than the slow Hawking mass loss. Only after it has been slowed down and neutralized, transformed into a quieter, more Schwarzschild-like object, would the classic, patient Hawking evaporation of its remaining mass truly dominate. This means the silent fade we've been contemplating is actually the final, longest act of a much more complex performance. The largest black holes in existence may spend eons winding down from their dynamic, whirling prime before they even begin the multi-trillion-year process of dissolving into the void. Their story is not one of simple dissipation, but of a gradual calming, a settling of cosmic storms before the long, quiet night finally sets in. The very fact that we are here to witness these cosmic giants is not a random accident of time. Our universe is filled with stable, long-lived black holes because the laws of physics, the fundamental constants that govern reality, have conspired to make it so. The speed of light, the strength of gravity, the value of Planck's constant, these are not arbitrary numbers. They are the precise settings on the cosmic control panel that determine how everything unfolds. Tweak just one of them even slightly, and the story of black hole evaporation changes dramatically. If the gravitational constant were stronger, or if quantum effects were more pronounced, Hawking radiation could be a powerful, rapid process. Black holes would fizzle out in cosmic moments, evaporating almost as quickly as they formed. In such a universe, supermassive black holes could never accumulate. Galaxies would lack their gravitational anchors, their stars scattered into a formless haze without central engines to shape them. The grand, structured cosmos we see, with its spiraling galaxies and stellar nurseries, might never have emerged. Instead, we find ourselves in a universe where the numbers are just right, or more precisely, just slow. The evaporation timescales are so astronomically long that black holes become near-permanent features, stable for tens of billions of years. This stability is what allows them to sit at the hearts of galaxies, governing the orbits of billions of stars, creating the environments where solar systems like our own can slowly coalesce and evolve. Our existence in this specific era, the stelliferous era of shining stars and anchored galaxies, appears deeply connected to the patient slumber of these dark titans. This observation touches on a profound philosophical idea known as the Anthropic Principle. In its simplest form, it suggests that the universe we observe must be compatible with the existence of observers. We could not find ourselves in a cosmos where black holes evaporate instantly, because such a universe would likely be too simple, too chaotic, or too short-lived to ever give rise to planets, chemistry, and life. The incredibly slow fade of supermassive black holes is not just a curious fact of astrophysics. It may be a necessary condition for a universe complex enough to contemplate its own mysteries. It places our quiet contemplation of cosmic endings within a much larger, almost poetic framework. We are not merely passive witnesses to a random process. We are the products of a specific, delicate balance, living in the narrow window of cosmic time where the lights are still on. The architecture is majestic, and the deepest abysses are patient enough to let us study them. The silent evaporation of a black hole, therefore, becomes more than a distant fate. It is a signature of the kind of universe we call home, a universe finely tuned for both darkness and wonder. The silent fade of a cosmic titan presents a final, staggering thought experiment for a civilization that has mastered the galaxy. Picture a society not just 1,000, but billions of years more advanced than our own, a true Kardashev Type 3 civilization that commands the energy output of an entire galaxy. For such an entity, the universe would be a very different place. The stars, those familiar furnaces of our current era, would have long since burned out. The only significant concentrations of energy left in a dark, expanding cosmos would be the black holes themselves, slowly radiating their Hawking glow. Could this ultimate civilization not merely wait for that slow leak, but actively tap into it? Could they turn the evaporation of a black hole into a controlled power source? Theoretically, the answer might be yes, but the engineering required defies everything we know. One concept is an extension of the Penrose process, which describes how energy can be extracted from a rotating black hole's ergosphere. An advanced society could, in principle, lower objects into this whirling region of spacetime, let them split apart, and collect the amplified fragments that escape with more energy than they arrived with. This harvests the black hole's rotational energy, slowing its spin, but to tap the Hawking radiation itself, the civilization would need to manage something far more delicate. Imagine constructing a Dyson sphere not around a star but around a small, hot black hole. This would be a megastructure of unimaginable scale and resilience, completely encapsulating the evaporating object. Its inner surface would be designed to absorb the high-energy Hawking radiation, converting that furious output into usable power for computation, propulsion, or perhaps forms of existence we cannot fathom. They might even artificially feed the black hole with matter to maintain its mass at an optimal level, creating a steady-state engine. This is not a proposal, but a pure speculation that stretches the limits of physics and imagination. It asks us to consider that the slow, silent decay we see as an ending could, in the hands of a godlike intelligence, be transformed into a beginning. The faint quantum whisper at the edge of reality might one day become the hum of a galactic engine, powering the final chapters of a story written by minds we can scarcely envision. Our universe's patient timeline is not the only possible story. The silent evaporation we have traced depends entirely on the precise numbers that govern reality here: the strength of gravity, the quantum graininess of space, the speed of light. These are our local laws, but if we step outside our cosmic bubble into the speculative realms of modern cosmology, a far wilder picture emerges. Theories like eternal inflation or the string theory landscape suggest our universe may be just one island in a vast archipelago of realities, a multiverse. In this grander view, each bubble universe could have its own unique set of physical constants, its own fundamental rules. Imagine a reality where gravity is 10 times stronger, or where the quantum fuzziness of the vacuum is 100 times more pronounced. In such a place, the delicate equation for Hawking radiation would yield a dramatically different result. The temperature of a black hole would be far higher. Its evaporation would not be a slow whisper over eons, but a roaring, rapid process. A stellar mass black hole might fizzle out in a matter of years or even seconds, shining with the ferocity of a supernova. Supermassive giants might never have the chance to form at all, their potential seeds evaporating almost as quickly as they condensed from the primordial chaos. In those universes, black holes would be transient sparks, brilliant and brief, rather than the enduring anchors we know. This shifts our entire discussion. The multi-trillion-year fade of a galactic core is not a universal truth. It is a local condition, a direct consequence of the specific, finely tuned numbers that define our particular cosmic home. We have been studying a single, remarkably patient case study. This perspective is both humbling and exhilarating. It suggests that the ultimate fate of matter and spacetime is not written in one immutable law, but in a library of possible laws, each volume describing a universe with its own unique narrative of birth, structure, and dissolution. Our reality's preference for slow, silent endings might be a rare chapter in an infinite cosmic library, a quiet verse in a symphony of possibilities that includes both endless silence and sudden, spectacular flame. The mathematics of this cosmic fade can feel impossibly distant, a story of numbers too large to feel real. To bring it closer, let us think of a black hole not as a monster but as a balloon. Not an ordinary one, but a cosmic balloon of unimaginable strength, its rubber skin perfectly smooth and dark. This skin is the event horizon, the ultimate boundary. Inside this balloon is not air, but the compressed mass energy of countless suns, a weight that bends the very space around it. Now, in our everyday world, even the best balloon loses air slowly, molecules seeping through tiny gaps in the material. For our cosmic balloon, a similar seepage exists, driven by the quantum fuzziness of space itself. This is Hawking radiation, a nearly imperceptible leak through the fabric of the event horizon. Picture trying to watch a balloon the size of our entire solar system lose a single, tiny molecule of air. You could stare for 1,000,000 years and see no change at all. That is the scale of patience required. For a supermassive black hole, the leak is so fantastically slow that the balloon would appear perfectly static, not for millions, but for quadrillions upon quadrillions of years. The entire current age of our universe is but a single, fleeting moment in its multi-trillion-year deflation. This simple analogy, the leaking cosmic balloon, helps ground an abstract process in a tangible image. It captures the essence, a gradual loss against a backdrop of such immense scale that the process itself defines eternity. While no analogy is perfect, it reminds us that even the most extreme objects in creation obey a kind of quiet, persistent physics, a slow exhalation back into the void from which they came. The slow fade of a black hole is not just a scientific concept, it is a narrative one. This profound idea has seeped from the pages of physics journals into the very fabric of our stories, transforming how we imagine the cosmos in fiction. For decades in popular culture, black holes were terrifying vortices, one-way doors to oblivion or convenient portals to other realms. They were plot devices, simple cosmic monsters. The revelation that they evaporate, that they possess a life cycle measured in epochs, has given storytellers a richer, more melancholy palette. Now, narratives can explore not just the terrifying gravity of a black hole, but its profound patience, its quiet heat, and its ultimate, luminous farewell. This shift mirrors our own scientific journey, moving from seeing them as static holes to understanding them as dynamic, evolving entities. Writers of hard science fiction like Greg Egan have woven these concepts directly into their worlds. In his novel Child's Ladder, the far future landscape is shaped by the physics of quantum gravity and cosmic evolution, where the fate of information and the slow processes of the universe are central to the plot. The black hole is not a villain to be escaped, but a phenomenon to be understood, a piece of a much larger and slower puzzle. This introduces a new kind of scale to storytelling, the scale of deep time. When a narrative acknowledges that a supermassive black hole will outlast every star, it forces both characters and audience to confront a universe of almost unbearable vastness and patience. The drama is no longer about surviving the next hour near the event horizon, but about comprehending a time span where such an object itself is merely a temporary landmark. This influence extends to visual media as well. In an episode of the television series Doctor Who titled The Satan Pit, the antagonist is revealed to be an entity imprisoned at the edge of a black hole's evaporation, its jail slowly decaying over eons. The story leverages the idea of Hawking radiation not as a technical footnote, but as a ticking clock on a cosmic scale, a prison wall that is literally dissolving atom by atom. Similarly, the film Interstellar, while focused on time dilation, presents Gargantua not as a simple pit, but with a glowing accretion disk, hinting at the complex energetic processes that precede its eventual far future quietus. These narratives use the science to add layers of meaning, transforming the black hole from a setting into a character with a destiny. This character has a birth in the collapse of a star or the merger of giants. It has a long, dynamic maturity, feasting on gas and stars, shaping galaxies, and it has a death, a slow leak culminating in a final flash. This narrative arc gives the cosmos a biography, a story we can follow. It replaces the cold, static void with a universe that lives, changes, and even passes away on timelines that stretch our imagination to its breaking point. This cultural shift enriches our engagement with space. We no longer just fear the black hole's darkness, we contemplate its warmth, however faint. We do not just see an end, we see a transformation. By integrating these slow, silent processes into our myths, we practice a form of cosmic empathy, learning to care about events and timescales far beyond our own. It is a way for the human mind, bound by decades, to reach out and touch the edges of eternity, finding story and meaning even in the deepest fade. That final brilliant flash of gamma rays is not the end of the story, it is the beginning of the greatest mystery. When the light fades and the last of the Hawking radiation dissipates into the void, what, if anything, remains? Does the black hole truly evaporate completely, leaving behind only empty space and a memory in the cosmic ledger? Or does the process halt at the very last instant, leaving a stable, microscopic fossil, a permanent scar on reality? Our current laws of physics cannot answer this. They break down completely at the scales involved, where gravity and quantum mechanics collide with equal ferocity. To cross this threshold, we need the final theory, a complete theory of quantum gravity that we do not yet possess. So we are left with two compelling, speculative possibilities, each more profound than the last. In the first scenario, the evaporation is total. The black hole converts every last bit of its mass energy into radiation, and then simply ceases to be. The singularity, the event horizon, the entire warped geometry of spacetime around it, smooths out and vanishes. It is a perfect erasure, a cosmic object dissolving without a trace, as if it never was. This is a clean ending, but it raises haunting questions about the conservation of information and the nature of that final, singular point. The second possibility is that evaporation stops. When the black hole shrinks to a size near the Planck length, the fundamental graininess of spacetime itself may act as a barrier. Further decay becomes impossible. What is left is a remnant with a mass roughly equal to the Planck mass, about 20 micrograms. This is an almost unimaginably tiny object, yet it would contain the entire gravitational memory of a vanished cosmic titan. It would be incredibly dense, stable, and nearly impossible to detect, as it would not emit light or interact with ordinary matter in any significant way. Such an object would be a ghost, a permanent monument to a black hole's existence, drifting through an eternally dark cosmos. And here, speculation takes a breathtaking leap. These Planck mass remnants, produced in unfathomable numbers over the lifetime of the universe, could be the elusive dark matter that binds galaxies together. They would be the perfect candidate, massive yet invisible, a fossil population of the universe's darkest eras. Even more radically, some theories suggest such a remnant, a knot of unimaginable density, could become the seed for a new universe in its own right, birthing a new cosmic bubble in a greater multiverse. This is where our journey through slow evaporation leads, not to a definitive answer, but to the precipice of the unknown. The silent fade of the largest black holes forces us to stare into the abyss of our own ignorance. It shows us that by following the logical path of our best theories to its very end, we arrive at a cliffhanger written into the fabric of reality itself. The fate of these giants is the ultimate test, a question posed by the cosmos that we are not yet equipped to answer, reminding us that the greatest discoveries always lie just beyond the edge of the light. This ability to conceive of an ending so distant is a uniquely human form of time travel. Our minds can stretch across numbers like 10 to the power of 100, wrapping thought around durations that have no parallel in our lived experience. It is an act of profound abstract thinking, a mental exercise that builds intellectual humility. When we truly sit with the idea that a supermassive black hole will outlast every constellation, every planet, and every name we have ever known, our own timeline is thrown into a new, clarifying light. Our civilizations, with their millennia of art and conflict, become brief flashes. Our species, with its long evolutionary journey, is a momentary chapter. Even our durable planet, which has circled its star for over 4 billion years, is a temporary haven in this slow cosmic narrative. To study the silent evaporation of these giants, then, is far more than an astrophysical pursuit. It is a philosophical practice. It trains us to hold multiple scales of reality in our minds at once, to appreciate the vibrant, fleeting beauty of our present moment against the backdrop of an almost eternal patience. This perspective does not diminish our story, it enriches it. It connects our brief, brilliant consciousness to the grandest processes imaginable, reminding us that we are part of a universe that is not static, but always in a state of becoming and unbecoming. This is the ultimate value of thinking in deep time. It expands our sense of what is possible, fosters a reverence for the intricate laws that allow for both life and darkness, and gently situates our hopes and struggles within a story of magnificent, humbling scale. In contemplating the slow fade of the largest black holes, we are not just solving equations about the far future. We are practicing how to be cosmic citizens, finding meaning and connection in a universe of glorious, relentless change. Our journey ends not with an explosion, but with a quiet, profound realization. We have followed a single thread from the ghostly birth of particles at an event horizon to the ultimate darkening of the cosmos itself. The story of a black hole's silent evaporation is far more than a physics lesson. It is a meditation on scale, time, and the beautiful impermanence woven into the fabric of everything. These giants, which seem like eternal anchors in the night sky, are in truth patient participants in a cosmic cycle of transformation. Their slow fade, governed by the subtle interplay of quantum uncertainty and gravitational might, reshapes our understanding of endings. Nothing is built to last forever, not mountains, not stars, and not even the deepest gravitational wells in existence. This truth connects the fate of a black hole to our own fleeting moment of awareness under the stars. By contemplating their multi-trillion-year farewell, we learn to see the universe not as a static museum, but as a dynamic, unfolding story where change is the only constant. The study of this process of Hawking radiation and information paradoxes is more than an academic pursuit. It is humanity's way of reaching across the eons, using mathematics and imagination to listen for the faintest whispers of reality's deepest laws. While our telescopes may never catch a supermassive black hole in the act of fading, the very idea illuminates the profound connections between the very small and the very large, between heat, light, gravity, and time. It reminds us that the cosmos is filled with quiet, patient dramas unfolding on timescales beyond our own, each one a piece of the grand puzzle. If this exploration of cosmic decay and ultimate transformation sparked your curiosity about the universe's hidden rhythms, we would love to hear your thoughts. Share what fascinated or surprised you most in the comments below, and subscribe for more journeys into the heart of space's greatest mysteries.